It's 1973, and Cummins Engine Company is about to make the biggest blunder in their 54-year history. They were preparing to launch a new heavy-duty V8 diesel aimed at both farming and other major industries, which promised to offer high horsepower and torque for demanding applications. But deep in their Columbus, Indiana engineering labs, warning signs were already flashing red. This is the story of the Cummins 903 V8, a bold experiment that promised brute power but ultimately left behind a trail of cracked cranks, blown budgets, and broken trust across America's farm fields. To understand the 903's spectacular failure, we need to go back to the early 1970s, when American agriculture was experiencing a mechanization revolution. Farms were getting bigger, equipment was getting heavier, and the demand for horsepower was skyrocketing. John Deere, International Harvester, and Case were all scrambling to build more powerful tractors and combines to meet this demand. Cummins had been powering farm equipment for decades, but mostly with their proven inline-six diesels. These engines had earned their stripes in trucks and stationary equipment, but the new generation of agricultural machines demanded something more: a bold leap in power. Cummins saw an opportunity to raise the bar with a purpose-built V8 that promised to outmuscle anything else on the farm. That bold leap took shape in the form of an ambitious 903 cubic inch, 14.8-liter diesel built from the ground up for serious output. Rated at up to 320 horsepower and around 700 pound-foot of torque, it was engineered to dominate the high-horsepower farm market with brute strength and modern flair. On paper, it looked like the perfect answer to agriculture's power demands. But Cummins was rushing to market with an engine that many felt hadn't been properly tested for agricultural applications. Internal development schedules show that the 903 went from concept to production in just 18 months. Half the time normally required for a completely new engine design. The pressure to launch came from Cummins' top management, who were watching competitors gain market share while Cummins remained stuck with their smaller inline engines. One executive memo from the period stated, "We cannot afford to let this market opportunity slip away. The 903 must launch on schedule regardless of testing status." From the very beginning, the 903 V8 was built on a foundation of compromises that would prove catastrophic in real-world use. Cummins took their proven inline-six architecture and essentially cut it in half, creating two banks of 4 cylinders each. But this seemingly simple approach created problems that the engineering team either didn't anticipate or chose to ignore. The crankshaft became the engine's Achilles heel. Unlike a true V8 design that's engineered from the ground up, the 903's crankshaft was essentially a modified version of their inline-six unit. The additional stress of the V8 configuration, combined with the massive torque loads of agricultural applications, created stress concentrations that the crankshaft simply couldn't handle. The crankshaft was supported by 5 main bearings, a typical design for V8s in its class, though some critics argued it was pushed to its limits under heavy stress. Compounding the issue, the journal's spacing and firing order, originally optimized for inline configurations, led to uneven loading and vibration issues in the V8 layout. Post-release analysis reportedly found the crankshaft faced stress levels well above design expectations, raising serious concerns about its durability in agricultural use. The analysis concluded that crankshaft failure could occur under sustained high-load conditions, exactly the conditions the engine would face in farming applications. The cylinder liner design presented another critical flaw. The 903 used wet cylinder liners, removable sleeves that formed the cylinder walls and were sealed at the bottom by O-rings. This design worked adequately in trucking applications where engines operated at relatively steady RPMs, but agricultural use involved constant load changes that caused the liners to shift and flex. The liner sealing system couldn't cope with the thermal cycling and vibration of agricultural work. O-ring failures allowed coolant to leak into the cylinders, causing catastrophic engine damage. Even worse, the liner movement caused bore distortion, that led to excessive piston ring wear and oil consumption. Agricultural equipment operates in some of the harshest conditions imaginable: dusty fields, high ambient temperatures, and sustained high-load operation. The 903 was a furnace of an engine. When cooling systems weren't engineered with precision, especially by some OEMs cutting corners or underestimating its needs, the result was inevitable: overheating in the field and angry farmers staring at steam instead of harvest. The engine's V8 configuration created hot spots between the cylinder banks that the cooling system couldn't adequately address. The water pump, sized for trucking applications, couldn't always move enough coolant to prevent localized overheating. Cylinder heads would warp, head gaskets would fail, and engines would seize from thermal damage. The radiator requirements for the 903 were massive, nearly twice the size needed for comparable inline engines. Many equipment manufacturers underestimated these requirements, installing inadequate cooling systems that guaranteed overheating problems. Cummins knew about these cooling demands but failed to adequately communicate them to OEM customers. Field reports from the first harvest season revealed that 903-powered combines were overheating so frequently that many farmers had to stop work during the hottest parts of the day. Some operators resorted to running their engines at reduced power to prevent thermal damage, negating the very power advantage that justified the engine's complexity. The 903's fuel injection system was another area where Cummins appeared to cut corners to meet their aggressive launch schedule. The system mirrored a dual inline approach, effectively two pump systems synchronized to work together, a configuration that created timing and balance problems from day one. The fuel injection pumps had to be precisely synchronized to prevent the engine from running rough or producing excessive emissions. But the synchronization process was complex and required specialized tools that most service facilities didn't possess. When the pumps fell out of sync, which happened frequently due to wear and vibration, the engine would develop a severe shake that could damage the entire machine. The fuel system's complexity made field repairs nearly impossible. A failed injection pump meant the entire machine was down until specialized technicians could be brought in. During critical harvest periods, this downtime could cost farmers thousands of dollars in lost productivity. Fuel consumption for the 903 was notably higher, often 10 to 20% above comparable inline engines, leading to dissatisfaction for some operators in high-load or extended-use situations. The poor fuel economy, combined with the engine's reliability problems, made it an economic disaster for farmers. One of the 903's most damaging characteristics was its excessive vibration. A problem that Cummins knew about but chose not to address adequately. The engine's firing order and crankshaft design created vibration patterns that were particularly destructive to agricultural equipment. Unlike truck applications where engines are isolated from the chassis by sophisticated mounting systems, agricultural equipment typically mounts engines directly to the frame. The 903's vibration was transmitted directly into combines, tractors, and other machinery, causing premature failure of everything from hydraulic lines to electronic components. The vibration problem was so severe that some equipment manufacturers had to redesign their entire chassis to accommodate the 903. Those who didn't experienced catastrophic failures of structural components, leading to expensive warranty claims and customer dissatisfaction. Cummins' own testing revealed that the 903 produced vibration levels much higher than their inline engines, but this information seems to have been buried in technical documents that most customers never saw. Sales literature emphasized the engine's power output while completely ignoring its destructive vibration characteristics. When the 903 finally hit the fields in full force by 1974, it turned heads with its power, but not always for the right reasons. Farmers reported excessive fuel consumption, aggressive engine noise, and unsettling vibration that hinted at deeper long-term reliability issues. While full-blown crankshaft failures were rare, confidence in the engine was already cracking. One of the more serious failure modes involved crankshaft breakage. In some cases, farmers reported engines seizing mid-operation with a violent shudder, followed by total power loss. While not widespread, when crank failures did occur, they could be destructive, sometimes damaging nearby components and sidelining machines during critical harvest windows. A particularly notorious incident occurred in Kansas during wheat harvest. A custom crew running 6 903-powered combines allegedly suffered 4 engine failures in a single week. Whether from hard use, poor cooling, or bad luck, the impact was the same: missed contracts, financial loss, and a damaged business reputation. The cylinder liner issues were more insidious. Coolant seepage into the cylinders often went unnoticed until performance dropped and damage became irreversible. Many operators only realized the extent of the problem once it was too late, and repair costs often approached that of a full replacement. According to multiple operator accounts, Cummins service techs were stretched thin during those early seasons. Parts availability was inconsistent, and downtime during harvest meant not just frustration, but real financial loss. Rather than acknowledge the 903's fundamental design problems, many of the company's field representatives attributed crankshaft failures to overloading or improper operation, despite the fact that the engines were failing under normal agricultural loads. Service responses frequently shifted blame to operators or OEMs, often denying warranty claims even when engines were used within spec. While Cummins engineers scrambled to address core reliability concerns, the company rolled out only minor updates, rather than making significant design changes. Meanwhile, many field technicians continued attributing failures to operator error or improper installation. Whether due to corporate caution or realism, public acknowledgement of deeper design issues remained notably absent. Equipment manufacturers who had initially embraced the 903 began to revolt as warranty claims mounted and customer complaints poured in. John Deere, one of the engine's biggest customers, conducted their own investigation into the failures and reached damning conclusions about the engine's design. Some industry insiders claimed that early failure rates approached catastrophic levels, prompting Deere to quietly discontinue using the engine and conduct their own analysis. International Harvester reached similar conclusions and began quietly switching back to their own engines for new equipment. Case followed suit, leaving Cummins with a rapidly shrinking customer base and a reputation in ruins. The OEM defections created a vicious cycle for Cummins. As major manufacturers abandoned the engine, production volumes dropped, making it even more difficult to justify the engineering investment needed to fix the engine's problems. The 903 was becoming an orphan engine with no future. Analysis of failed 903 engines revealed the full extent of the design problems that Cummins had tried to hide. Independent teardown reports pointed to stress concentrations at critical crankshaft points, far exceeding what the V8 layout could reliably handle. The crankshaft material itself was inadequate for the application. Cummins had used the same steel specification as their inline engines, but the V8 configuration required a much stronger material to handle the additional stress. The company had chosen to use existing materials to save costs, knowing that strength would be marginal. The cylinder liner failures were traced to inadequate sealing design and poor quality control in manufacturing. The O-rings used to seal the liners were made from materials that couldn't withstand the thermal cycling of agricultural use. Even worse, the manufacturing tolerances were so loose that proper sealing was impossible, even with good O-rings. Post-launch service and field reports indicated that some cooling systems installed under-spec'd for the V8's demands struggled to manage hotspots, particularly between the cylinder banks, pointing to thermal management issues in real-world use. As the 903's problems became undeniable, Cummins attempted a series of engineering fixes that were too little too late. The company introduced a stronger crankshaft in 1976, but the new design still couldn't handle the stress concentrations created by the flawed architecture. A revised cylinder liner design was introduced in 1977, featuring improved sealing and better materials. But the fundamental problem of liner movement under load remained unsolved, and failures continued at unacceptable rates. The most significant change was a complete redesign of the cooling system, including larger water pumps, improved flow patterns, and better heat dissipation. While this reduced overheating problems, it couldn't address the engine's other fundamental flaws. Each fix required existing customers to pay for expensive retrofits, further damaging Cummins' relationship with the agricultural market. Many farmers chose to repower their equipment with competitive engines rather than continue dealing with the 903's problems. By 1978, the agricultural market had completely rejected the 903 V8. New equipment sales had virtually stopped, and the used equipment market was flooded with 903-powered machines that nobody wanted to buy. Resale values for equipment with these engines were 30 to 40% lower than comparable machines with other engines. Farmers who had invested in the technology found themselves stuck with equipment that was nearly worthless on the used market. The engine's reputation was so toxic that some equipment dealers refused to accept 903-powered machines as trade-ins. The mere presence of a Cummins V8 under the hood was enough to kill a sale regardless of the machine's overall condition. Custom harvesters, who depended on reliable equipment to maintain their businesses, abandoned the 903 en masse. The engine's unpredictable failures made it impossible to maintain harvest schedules, and the resulting business losses forced many operators out of the industry entirely. Perhaps the most damaging aspect of the 903 saga was Cummins' handling of existing customers after the engine was discontinued. Rather than taking responsibility for the design flaws, the company essentially abandoned its owners to deal with ongoing problems on their own. Parts availability became a major issue as Cummins reduced production of 903 components. Critical parts like crankshafts and cylinder liners became increasingly difficult to obtain, forcing owners to cannibalize other engines or seek expensive aftermarket alternatives. Service support was equally problematic. Cummins trained fewer and fewer technicians on 903 repair procedures, making it difficult for owners to find qualified service. Many dealers simply refused to work on the engines, claiming they were too problematic to service profitably. The company's final insult was offering upgrade programs that allowed 903 owners to replace their engines with newer Cummins models at full retail price. Customers who had already paid premium prices for the 903 were expected to pay again for engines that actually worked. The 903's failure had far-reaching consequences that extended well beyond Cummins. The disaster reinforced the agricultural industry's conservative approach to new technology and made farmers extremely skeptical of unproven engine designs. Equipment manufacturers became much more cautious about adopting new engines, implementing extensive testing programs that added years to development cycles. The mixed market response to large V8s, including the 903, contributed to a later industry preference for high-torque inline-six engines in agriculture. The failure also damaged relationships between engine manufacturers and equipment builders. OEMs became much more demanding about warranty coverage and technical support, knowing that engine problems could destroy their own reputations with customers. Cummins' reputation in agriculture was so damaged that it took the company nearly a decade to regain significant market share. Even today, some farmers remember this disaster and remain skeptical of Cummins' agricultural engines. The 903 V8 wasn't just a failed engine, it was a betrayal of trust that revealed how a respected manufacturer could prioritize profits over customer welfare. Cummins promised farmers the ultimate power solution, but delivered a mechanical nightmare that destroyed crops, businesses, and lives. The engine didn't die from natural causes. It was murdered by corporate greed, engineering shortcuts, and a cover-up that made the problems worse.